Good evening. As you know, my name is Austin Eubanks, and today I'm presenting my talk titled, It's All the Same, but This Way's Better, How I Learned to Stop Worrying and Love the General Linear Model. This talk is pre-recorded video because I was having some problems with Zoom lagging real bad. So I went ahead and pre-recorded it. I uploaded it to my YouTube page, UArk Psych Stats, and now what you're watching is just me screen sharing that YouTube video. But it runs about 50 minutes. We'll have about 10 minutes for questions at the end. I do ask that if you have any questions, just jot them down along the way, and when we get to the end, we'll talk about them. And I'll be hanging around after the hour is over, so if anybody has any questions that we can't fit into that last 10 minutes, then I'll be around as long as people have questions. But that said, we'll just go ahead and jump right in. And first, I'll apologize for having pretty wordy slides. I've learned over the last few weeks teaching multivariate online that my and many of your internet connections are pretty terrible, and there's audio lag issues and things cut out. So I want to make sure that nobody's missing any information. Plus, the slides are available. There's a link on the final page that will get you there. And so if anybody goes back to check out those slides again, I want to make sure that you're not limited to what you can remember me saying as I was on any given slide, and instead that information is there and it's available for you. I want to make it clear that the distinction that was made in the last farm that somebody was talking about, the R versus SPSS thing, but that's not right. What we're talking about is not R versus SPSS. It's the conceptual way that you think about statistics. It's linear modeling versus what I call the classic stats, the ANOVA and t-test, etc. Although R is a million times better, but that's a completely different conversation. The take-home point from today is that certainly at the graduate level, but even at the undergraduate level, we should shift to primarily teaching and thinking about statistics in terms of linear modeling instead of as those classic stats. And what I hope to convince you of today, that what you walk away from today is realizing that all of these parametric tests that we know and love are just general linear models. I'm not saying you can substitute and that general linear models are comparable. I'm saying they are literally, exactly, directly one and the same mathematically and conceptually. In terms of limitations, I'm sorry if you were hoping to hear about repeated measures and mixed effects models, which repeated measures are just mixed effects models. We don't have time to get into that today. That might be another talk or workshop, something down the line. But just, I will say that if you understand the general linear model, making that jump to mixed effects models and repeated measures is pretty simple and straightforward. I'll also mention one of the benefits that I'm not going to get into of general linear models is that it can also handle the non-parametric counterparts of all these tests. So the independent samples t-test, the non-parametric version of that is the Mann-Whitney U, and you can do Mann-Whitney U tests using general linear models with just one small tweak. So the general linear model has a lot of functionality beyond those classic stats in that way as well, but we're not going to really get in that too much today. But that said, why should I care? Why should you care about the general linear model? Why should you care about what I have to say? And the answer is because we're cognitive misers. Our brains love efficiency. It loves low effort. And when there is one single cohesive framework for answering all of our statistical questions, that's more efficient. It's easier to learn. It's easier to understand than this needlessly complex approach of teaching these separate, discrete, classic categories of analyses. Beyond that, linear models are linear models. You can move a linear model out of frequentist inferences altogether and into Bayesian and other methods, and the linear model itself is going to operate the same way. Beyond that, for the mentors out there, I don't think it's a wild presumption that you care about your students learning all this fandangled statistics stuff. And learning that general linear model framework facilitates more easily learning the more advanced techniques, because strategically, thinking about just basic statistics in terms of statistical modeling and model comparisons and stuff means when you move into the more advanced techniques that are also statistical modeling, model comparisons and stuff, it makes that an easier jump to make. And then tactically, just learning R as part of learning basic statistics means that when Bill or Anna or future colleagues coming into the department teach those more advanced stats techniques, instead of wasting class time teaching basic R use, they can devote the entirety of their time to teaching the actual course content, which will facilitate a deeper understanding of those more advanced techniques. I also argue that if we had an undergraduate, advanced or honors statistics course that taught GLM and taught basic R use, that would look good on them as far as applying for grad schools and interviewing and things like that. For reasons not to take the general linear model approach, I legitimately can't think of any. When I was in the Marine Corps, we had a term that we called the monkey factor, and that's when you say, well, why do we do this way? And the answer is because that's the way it's always been done. That's the monkey factor. And I made a name and career for myself fighting the monkey factor because I don't believe that if there is a better way of doing something, whether it's faster, it's cheaper, it produces a better product, it's more efficient, whatever metric you want to use for it being better, if there's a better way of doing something and there's not an explicit or specific reason to not do it that better way, then I believe you should do it that other way, and that you should not stick with the status quo simply for the sake of sticking with the status quo. I'm sure if you go back to the late 1920s, you can find researchers who say, I don't know about this Fisher's ANOVA stuff, just make separate correlation tables for men and women so that we can look for differences that way. And so I don't buy that. I don't accept that we should stick with the status quo just because it is the status quo. So to demonstrate how efficient this can be, what I'm going to attempt to do is teach a crash course in graduate level statistics in just 30 minutes over this next, for the rest of this talk. So first I need to start by defining a few things here and going over what the data is that we're going to be talking about. So in terms of the definitions, first we have parameters. I'm going to be saying parameters a lot. Parameters are just bits of things that you're putting in your model to predict some outcome. It's your variables, so your independent variable, your predictor, your parameters, whatever. Then augmented versus compact models. Your augmented model is the full model. It has all the variables in the analysis, all the variables of interest. Your compact model takes that augmented model, but it pulls out one focal parameter. And we'll talk about what a focal parameter is, but what you really need to know is that your augmented model has everything in it, and then you pull out one specific thing to make your compact model. And then you're just comparing your augmented versus your compact model to look for the effect of that one focal parameter. In terms of the data that we're going to be talking about, it's a real simple design where participants watch some videos and the outcome, the dependent variable, is their mean laughter across 7 videos. They watch the videos either with fellow in-group Razorback fans or with rival out-group LSU fans. Participants were either male or female. We also got a continuous measure of how much they liked the group that they were with. And then we took a measure of how many alcoholic beverages they had had on that particular day. So the first question might be, were the videos funny? And if funny is operationalized by laughter, then the question is, was there laughter, or was the mean of laughter significantly different from 0? This is a one parameter model or an intercept only model, which is the same as a one sample t-test. So if we look at this as a one sample t-test in SPSS, here's what our output looks like. And here's what the output looks like running it as a general linear model in R. And so we have this LM parentheses, that's our linear model function, and then we put in some formula. So this tilde means is regressed on or is predicted by. In R, in linear formulas specifically, the intercept is represented by the digit 1. So what this says is our outcome laughter predicted by the intercept, not predicted by the number 1. And this is a one parameter model because that is the only parameter that we have in here is that intercept. So first thing to point out is that these are mathematically identical. Our t is 31.61. Over here you see our t of 31.61. Our degrees of freedom, 209 and 209. Our p is less than 0.001. P is less than 0.001. And then this shows our mean difference of 5.91, which is our intercept here. So what this is really doing, what this linear model is doing, is using this value of 5.91 to predict all of these different outcomes. So if we predict 5.91 for this dot right here, and then if you imagine drawing a red line between that dot and this prediction line, this green line that's at 5.91, that red line would be the error for that particular prediction. And then we go to this point here, and if we draw a red line between the actual value plus its predicted value of 5.91, we have the error for that one. If we do that for all of these different points, and then square all of those red lines and sum them all up, we have our sum of squared errors. So here what we're doing is we're taking that intercept and just systematically varying it between 0 and 13 and continuously recalculating that sum of squared errors. And you can see that the sum of squared errors has this parabola shape, and that there's a certain point where that error is at its absolute lowest point, which coincides with that mean value of 5.91. Now, the reason for that is because we know that data is evenly distributed on either side of the mean in a normal distribution, but another way to think about that is that our error is evenly distributed on either side of the mean in a normal distribution. So what this one parameter model is testing is if we include that intercept of 5.9, which gives us this error down here, does that significantly reduce error beyond just predicting 0 for every value, which gives us our sum of squared errors up here? And is that reduction in error significant? And the answer is yes, which is what that t-test and that p-value gives us. By predicting 5.9 for every one of these dots, we reduce error significantly above and beyond predicting 0, which means that our mean is significantly different from 0. So the next question might be, what is the relationship between how much people laughed and how much they liked the people that they were around? So now we're going to have a 2-parameter model because we're going to include that intercept, but also some second parameter, in this case, the slope of this liking variable. Because it's a continuous variable, that makes this the same as a correlation. So if we run this as a correlation in SPSS, here's what our output looks like. Our correlation is 0.312, our p is less than 0.001. When we run that as a linear model in R, again, here we have our 2 parameters, our intercept plus the slope of liking. And so 2 parameters in our model, thus 2-parameter model. Now you'll notice again, mathematically, same thing. P is less than 0.001, and we have our R squared down here of 0.0972, and if you take the square root of that, then you get our correlation of 0.312. And you may be asking why it is that you have to take this extra step of taking the square root of your R squared in order to get the correlation. And the answer is because correlations are computed based on standardized variables. So if instead you standardize these variables by wrapping them in scale, which is just the standardizing function. So this linear model is standardized laughter regressed on the intercept plus the slope of standardized liking, and now you can see that our slope is that correlation of 0.312. And so here all I'm doing is I have that mean of our laughter of 5.91, and so I've locked in that mean here with this green line, and instead of varying that intercept up and down, I'm just allowing that slope to change back and forth. And what you can see is we have a similar thing as before, where the sum squared error has this parabola shape, and that there's a certain point where that error is absolutely minimized, which is at that slope of 0.62. And once again, if these were standardized, then that error would be maximally reduced at the correlation between these two variables at 0.312. So what this is really testing here is, does using the slope of this blue line to predict all of these values of y significantly reduce error beyond using the slope of this red line to predict all of these values of y? So this red line is our compact model. It is the intercept only model. And so if we look here where we have on this top line laughter predicted by the intercept only, if we use this red line and we draw more red lines between each dot and this red line here, square them, sum them all up, that error will come out to be 1533. By contrast, if we use this blue line here to predict all of these values and then draw a red line between each dot and that blue line, square them, sum them all up, now our error is 1384. Which is a significant reduction in error. Our R squared goes up by about 0.1, and here we have F equals 22.39, P is less than 0.001, and mathematically, this T and this F are exactly the same. F is just T squared. R allows you to choose whether you want it to output the T values or the F values, but they're the same. Throughout this talk, I stuck with whichever one SPSS outputs, but all this is testing then is with this focal parameter of liking, if we include all the parameters in this coefficient table, which in this case is only 2 parameters, as our augmented model, and if we remove this focal parameter of liking, that becomes our compact model. So does the augmented model of including both of these parameters significantly reduce error beyond the compact model that leaves out this focal parameter? That's what this t-test here is testing. Does including that augmented model, that focal parameter of the augmented model, significantly reduce error beyond leaving it out? So you might ask, was there a difference between how much men and women laughed? So we're going to do another 2-parameter model, but this time we're going to have a dichotomous parameter instead of that continuous liking parameter that we used last time, which makes this an independent samples t-test. So if we run this in SPSS, here's what the output's going to look like, and here's what the output looks like in R. Again, we have our 2 parameters. We have our intercept, and we have the slope of gender. So again, mathematically, these are the same thing. We have our t is negative 3.11, t negative 3.11, our p is 0.002, p is 0.002, degrees of freedom is 208, and our mean difference of negative 1.14 is our slope for gender. Now, real quickly, I'll point out that I mentioned that you can do all of the non-parametric counterparts to the parametric test. So in this case, an independent samples t-test, the non-parametric test is Mann-Whitney U. And the only difference as far as a general linear model is concerned is that instead of having your outcome be that raw value of average laughter, is if you take all 210 of your participants and sign rank, so you rank them from lowest to highest amount of laughter and give them that value of 1 through 210 based on rank ordering their laughter. And so when you assign signed ranks or ranks to your different variables, that's how you get those non-parametric tests. But the point is, just real briefly, that you can also do all your non-parametric tests as general linear models. But one of the best things about general linear models, as far as I'm concerned, is the way that it allows you to visualize your data. And that helps to me more intuitively understand what your output, what your results are telling you, and what your data is trying to tell you. So here we have females coded as 0, males coded as 1. And all I've done is plotted all their values on the y-axis here for how much they laughed. And I'm going to jitter those points to the left and right. So nothing's changed besides shifting them to the left or right so they don't all completely overlap. And then we add in our intercept. Now, because your intercept of 6.5 is just the mean where x equals 0, that means that our intercept is the mean of females. So now for a 1 unit increase in x, y is predicted to decrease by 1.14, which is why that slope is negative 1.14. So by asking, is this slope different from 0, you're really asking, is the mean of males significantly different from the mean of females? Or another way to ask it is, does the augmented model significantly reduce error beyond the compact model? And that's what we're looking at here. So with our compact models, this green line, and if we just use this green line right here, this value to predict all of these, get all of our red lines, square them, sum them up, and then over here we use that same green line to predict all of these, get all of those red lines, square them, sum them up. Our sum of squared errors is 1533. That's that compact model. By contrast, if we instead use this blue line to predict all of our values, so over in this group we're still using that same value to predict all of those values, but over here in this group, instead of using that green line right here, we're going to use this value right here to predict all of these dots. And that instead reduces our error to 1465, which increases our r squared by about 0.04 and is a significant reduction in error. So once again, what this t-test here, if you square this, it will be your f at 9.7 and your p is still 0.002. So this is testing, does including this slope for this focal parameter, does that significantly reduce error beyond leaving it out and just including everything else that's in the model? And the answer is yes, it does. Next we may ask though, is there really a gender difference, or is it just that females didn't really laugh more because they thought it was more funny, but maybe they're just more sociable and nice and friendly, and they liked the people that they were with more. And so after we control for liking, is there still a difference between men and women? So now we have a 3-parameter model that's using both a dichotomous and a continuous parameter, which is the same as an ANCOVA. And so first I want to point out that there's nothing special inherently about a covariate. A covariate is just some variable that you're including in a model that you want to control for, but you're not necessarily interested in interpreting what that parameter estimates. And so once again here we have the exact same thing in R and SPSS. I'm not going to waste a lot of time pointing it out point by point, and I just hope that you take me at my word that these things line up perfectly. But now, instead of, for the visualization, instead of randomly jittering things left and right like this for visual purposes, I'm going to systematically vary things to the left and right, specifically based on that third variable of liking. So both for females and for males, I have things jittered off to the left and right from that midline based on that liking variable. So zeros are over here on this side, and as it moves this way, their liking is increasing. Same thing for males, that it's zeros over here and increasing as it moves this way. So we have some information, we know some information about what we would predict from somebody's laughter based solely on that liking variable, which is that for each 1 unit increase in liking, we predict that their laughter is going to go up by about 0.6 seconds. So where that's 0, we don't change their predictions any. Where liking is 1, we're going to add 0.61 seconds to their laughter. Where liking is 2, we add 1.22. All the way up to where liking is 6, we're going to add 3.66 seconds to their laughter. So all we're going to do is take this point here and bump it up here. Now you notice over here where it's 0, there's no change in their prediction for laughter. And where it's 1, you just get this real small bump, but where their liking is a lot, you get a much bigger bump. So here's what it looks like now. So before it was down here, and now it's up here. So this is what the data look like after controlling for that liking variable. So when you visualize this plot right here, this already has information about controlling for that variable of liking. So now when we look at that slope of gender to test for gender differences, it's now testing for gender differences after controlling for that liking parameter. So here once again, now we have our compact model that is just the intercept plus the slope of liking, which even though you can't see that slope here, it's already included because these points have been shifted up based on that liking thing. So by having just this green line, the intercept only, it already includes that information about their liking. So the compact model is just the intercept plus the slope of liking, and the augmented model is that intercept plus the slope of liking plus the slope of gender, which is this blue line here. So once again, all we're testing is if we use this green line here to predict all of these values and use that same green line to predict all of these values, that's our compact model. That is just the intercept plus the slope of liking. That gives us a sum of squared errors of 1384 here, our SSE compact. And then the augmented model also includes this blue line here, that slope of gender. And so when we also include that slope of gender in our augmented model, we can see that reduces our sum of squared errors to 1321. So instead of predicting this point here for all of these values, we're going to predict off this blue line for all of these values. It does significantly reduce our error as evidenced by this F test, and you'll notice here that I did output F instead of T, and that this F test lines up perfectly with this. Now I'll also point out that if you did this the opposite way, it would work out the same. If we would have made that adjustment based on gender and then looked at our slope of liking, the only difference is that here the compact model would have been the intercept plus the slope of gender, and the augmented model would have been the intercept plus the slope of gender plus the slope of liking, and then this F test down here would have been this 22.58 instead of this 9.8 0.93 that we have here. Because again, what this is doing is this says like, all right, so our augmented model has all three of these parameters in it. So in a model where the focal parameter is gender, if we take out gender to make a compact model and compare that against a model that has all three, is that a significant reduction in error? And yes, it is. Our F is 9.33, P is 0.001. And then if we have a separate model that has all three of them as our augmented model and simply takes out, looks at the liking variable here, this parameter as our focal parameter, if we take that out to make the compact model and compare just these two versus all three of these, is that a significant reduction in error? And the answer is yes, F is 22.58. So again, all these things are doing is model comparisons, comparing a model that includes that parameter with versus one that removes that parameter but leaves everything else in that model. So here we can see that yes, even after controlling for how much people liked the group they were with, there was a significant difference between men and women. So next we might ask, was there a difference in laughter as a function of how much they liked the people they were with and how much they drink? So we have another 3-parameter model, but this time it's 2 continuous variables, which is the same as multiple regression. So what this might look like, if you run it as a multiple regression in SPSS, is this right here, and then again here in R we've got our 3 parameters, our intercept, our slope of liking, and our slope of the number of drinks that they had. And once again, all the numbers line up perfectly. I'm not going to waste time pointing them out point by point and just roll right into the visualization. So here we're going to do something similar as we did before, but instead of having a group for females over here and a group for males over here, is we have a continuous X variable of liking here on this x-axis, and then I have them colored by the number of drinks that they had, starting from red, fading to white, and then on into blue, where somebody who had 0 drinks is going to have a dark red spot, up to somebody who had 10 plus drinks is going to have those dark blue spots. And then we have some information about the predictions that we have for how much they laughed based just on how much they drank, and that prediction is 0.5. So for every 1 drink increase, we predict that their laughter will go up by half a second. Where somebody had 2 drinks, we predict an extra second of laughter. Up to somebody having 10 drinks, we predict 5 extra seconds of laughter. So we can make those same adjustments like we did before. You see where somebody had 0, we're not adjusting their prediction for laughter any, but where somebody had, say, 10 drinks, we're making a much bigger adjustment on their laughter. And so again, just bumping all of those points up, and now here's what it looks like after including that information about drinks. And now we're able to fit that line, that intercept for liking, and test for significant differences. So once again here, our compact model is this blue dotted line that runs across the screen, and all that compact model is the intercept plus the slope of drinks. And again, even though there's not an actual slope line on this screen, that information is in there because we already shifted those points up based on the number of drinks that they had. And so our augmented model is this green line here, where it also includes that slope of liking. And so if we take this dotted blue line here and we predict all of these different values based on just that flat blue line, our sum of squared errors is 1188. By contrast, if we instead use this green line to predict all of these values, which is our intercept, our slope of drinks, plus that slope of liking, our sum of squared errors drops down to 1027, our R squared goes up by about 0.1, and that is a significant change. F is 32.5, P is less than 0.001, and you see here, once again, I outputted the F's, and that F test lines up perfectly because this is that F test right there. This is testing, okay, the augmented model is all 3 of these parameters, with a focal parameter being this liking variable. If we take that parameter out and make a compact model that has just the intercept plus the slope of drinks, what is the sum of squared errors? And then if we put that focal parameter back in to make the augmented model, does that augmented model significantly reduce our sum of squared errors? And the answer is yes. And then if we did it the other way, and we had a augmented model that had all three of these parameters, and then our focal parameter is this drinks variable, and if we take that focal parameter out to make a compact model that only has the intercept plus the slope of liking, what's the sum of squared errors, and is that sum of squared errors significantly reduced by putting that focal parameter back in and comparing that augmented model against the compact model? And the answer is yes. So now we'll look at one last model where we're interested in asking if there's a difference based on gender or in-group versus out-group, and whether these two things interact with each other. So we have a 4-parameter model with 2 dichotomous variables including their interaction, which is a 2-way full factorial ANOVA. So again, in SPSS, here's what the output's going to look like, and in R, here's what the output's going to look like. Notice that we have our 4 parameters, our intercept, our slope of liking, our slope of in-group, plus the interaction of gender and in-group, where in R, interactions are represented by a colon between the variables instead of with an asterisk between those variables. But once again, mathematically, these things all line up perfectly, so I'm just going to skip past talking about it and go right into the visualizations. And you may be expecting something kind of like this that we've done before, where you take all your points, you plot them out, and then you offset them based on some other variable, and now you have your new predictions, and then you fit some for some group difference of that other variable. But the difference is that before we didn't have an interaction. So what we did was here, both males and females have the same slope based on in-group or out-group. By including an interaction in a linear model, all that means is that you allow that slope to be different for males and females. So males and females don't necessarily have to have the same slope of in-group. So what that might look like is more like this. So now I've put in-group on the x-axis, and I've just pushed females to one side, males to the other side. Again, that's just to make it easier to visualize. What's important is that midline, because these are all coded as -half. These are all coded as +half. We have our average females in the in-group, average males in the in-group, average females in the out-group, average males in the out-group. And I'm simply going to put some lines on the screen here. Now, this black line is the slope, is that main effect of in-group versus out-group. So it ignores gender. And if you just take, if all of these points here were black, and you just take the mean of all of them, then this point right here is what would be the mean of all of those. Same thing down here, that if you just take the mean of all of these points and ignore them being red or blue, then right on that black line is where your mean is going to fall. So you can see that we have a main effect of in-group here, such that we expect higher, more laughter from that in-group than from the out-group. You also see a main effect of gender because that female prediction line is higher than our prediction line for males. But you notice that over here, the predictions for females is lower than the actual mean of females. We're under-predicting females in that in-group, and over here, we're over-predicting that mean of females in the out-group. And by contrast, it's the opposite for males, that over in this group, we're under-predicting the actual values, and over here, we're over-predicting those actual values. So putting that interaction in the model simply allows us to give those lines separate slopes and not force the males and females to have the same slope for in-group versus out-group, and so it would look like this. So now let's take a look at what our interpretations might look like. So here we have, again, males and females coded as -half, plus in-group versus out-group is coded as -half. And so first we look at that intercept. Because in-group and out-group are coded as -half and +half, then 0 is collapsing across those two things. So the values at 0, where x equals 0, is the values ignoring in-group versus out-group. Thus, our estimate here is when collapsed across gender and collapsed across in-group versus out-group, our average is 5.93. You'll hear some people call this the grand mean. That's not technically correct in this particular case because it's only the grand mean when you have equal n's in every group, but in this case we have more females than males, so it biases that estimate a little bit and it's not quite the exact grand mean. But regardless, our intercept here is the mean where everything is 0. So you'll notice that it falls directly between males and females on this side and males and females on this side. That main effect of gender, again, because in-group and out-group is coded as -half and +half, and 0 represents collapsed across that, then our difference between females and males, where x equals 0, is that intercept. This green line here represents a 1.16 second difference between what we predict for females and what we predict for males down here. The main effect of in-group is, again, that black line. So the difference between the black line here, that when we have a 1 unit increase in x, we predict a decrease of 1.99. And so that main effect of in-group is -1.99. And then finally, our interaction is the difference between differences. So if we look here at our actual group means, our females in the in-group averaged 7.79 seconds of laughter. Males were 6.07. So this orange line here represents 1.72 seconds difference between these two groups. Over here in this group, we have our females at 5.24 and our males at 4.64 represented down here, and the difference between those is 0.6. So this purple line here represents 0.6 seconds. And so then if you take the difference between those two things, the difference between this orange line and this purple line, that difference is 1.12 seconds. So our difference between differences here is 1.12 seconds. And if we look at these things side by side, here we have a 3-parameter model that just has the intercept, the slope of gender, and the slope of in-group. And then our 4-parameter model, that augmented model, is the intercept, the slope of gender, the slope of in-group, plus the interaction between the two. And so remember, that interaction is the difference between differences. Notice here, the difference between males and females is exactly the same as the difference between males and females here, because we're forcing those two to be the same, not allowing them to interact. When we interact, now there's a bigger difference between males and females here than there is over here. And that's because being in the in-group has a bigger effect on females than it does on the males. So again, our model comparisons, all it's testing is, if we look at this 3-parameter model, what's our sum of squared errors? And it's 1262. When we look at our 4-parameter augmented model, our sum of squared errors is 1245. It increases r squared by only 0.01, and we see that that's not a significant difference here. So including this interaction in the model does not significantly reduce error beyond just leaving it as our main effects only and looking at this as a multiple regression rather than as an interactive model. So in this case, we would say, no, there's not a significant interaction between these two variables. So in summary, there's no fundamental difference between all the different linear models that I covered today. They are mathematically and conceptually identical to their classic stats counterparts, but I argue that the general linear model framework is more efficient and easier to learn and understand because you're continually just adding one new piece of information to what you already know instead of learning some completely separate analytical technique. So whereas the classic stats approach does teach things as discrete categories of analytical techniques, but that GLM framework teaches the underlying framework of the classic stats, which gives you one method that answers all of your questions, that gives you one method for verifying all your model assumptions, one method for doing your case analyses to look for unusual cases and outliers, one method for visualizing your data, and all of this together leads me to argue that the GLM framework is a better and more efficient way of learning and thinking about statistics. Furthermore, once you have the basics of R down, running linear models in R is actually really simple and intuitive. as opposed to, say, SPSS, and this is regardless of whether you're using the point and click drop down menus option or typing in syntax. So for example, if you're just trying to run an interactive model and get some table means, this is how you would do it in SPSS, regardless of whether it's the point and click method or if you're typing syntax, whereas this is all you have to do in R. And call me crazy, but this seems a lot more efficient than either of those two other options over there. And so here is just a table kind of summarizing at a glance the difference between these linear models and their classic stats counterparts. And so the way I've broken it up here is X represents a continuous variable, G subscript D represents a dichotomous group, capital G represents a group that has 3 or more categories. But even that unnecessarily overcomplicates linear modeling, because in reality it's like this. Really, it's just your DV regressed on the intercept, or your DV regressed on some variable, or your DV regressed on some variable, or the time 2 DV minus the time 1, so the difference in DVs regressed on some variable, or the DV regressed on some variable, or the DV regressed on some variable, or guess what, the DV regressed on some variables. And so you don't even have to think about like those specific, it's very intuitive to use these linear models. And no matter, as I said before, no matter what type of variables you're putting in there, the intercept is just the mean outcome when all your predictors are 0, and then your slopes for your predictors is just the predicted change in that outcome based on a 1 unit increase in whatever that predictor is. But that said, R is own right a very valuable skill to have. It's an employable skill. R use is increasing, certainly when you look at like the data science community in terms of jobs, like R is far above and beyond SPSS and some others. But even in academe, SPSS has been on the decline. It peaked around 2009 and has been steadily plummeting for the last 11 years, and people are moving away from it. R is the future, and so I argue that maybe we would do well to make sure that our students are equipped with that tool that seems to be the up-and-coming tool that's going to be the way of that future. And so here we have our graphs just showing that R is increasing a lot in academe. Besides that, I don't know of anybody who will argue that R isn't the best, if not among like the top top 2 very best programs in terms of data visualizations, whether you're doing some sort of complicated multifaceted meta-analysis, decomposing three-way interactions of linear models, or here I had 14 different students that tried to p-hack to get the lowest p-value on some model, and then I ran it 100 times resampled on other models to see like what was that stability of their p-value. So again, like R is very, very, very good in terms of graphing. I even like to just have a little fun with my graphs, and so I graphed a comic strip looking at some instructions for how to make TiT with the nice XKCD package. I've also used R in my role as a lab manager. So here, just doing at-a-glance calendars for all our different RAs, broken down by like me, Scott, Derek, and David, and each of our RAs. We have their schedules in an Excel file already, so all we had to do is pull that in, write a few lines of code, and it spits out these calendars for me. And then in terms of, at the beginning of the year, we ask all of our RAs, we tell them what projects we're working on and ask them for their preferences so that we can try to assign them on projects that they want to work on most. And so, I probably shouldn't assign this particular RA to this one because they really weren't interested in that. Whereas this RA here, like they're really, really interested in that one project above and beyond the other. So maybe I should assign them to there. So again, like I've used it outside of my research. Same thing for designing studies. So here we ran a study where it was, the numbers task where there's a whole bunch of pages and there's a target. The target numbers are 13 and 47. And so they have to go through all these different pages and circle all of the occurrences of the numbers 13 and 47. Well, I wanted to digitize that, so I wrote an R script that prints out pages of 200 numbers that has exactly 8 random occurrences of either the number 13 or 47, which is their target numbers, so that I could just export those as images and upload them to Qualtrics and use that instead of having to do this pencil and paper. I've also programmed and run fully automated validated IATs in Qualtrics just using R. Demonstrated here. I've done one of these in our own lab, plus I got with Anna and helped her program an IAT for one of her studies. And then another thing was I've helped Connie and Morgan, where one of their programs will not output this specific information here, but they need that information. So their SOP was to sit there and just type in all of these numbers for each one of their participants. And I said, screw that, take some screenshots of the data, send it to me, and let me see what I can do. And sure enough, I wrote a script that extracts that information from the images that they sent us, runs across a folder, and with just a few lines of code, extracts all of that, combines them, and creates a data frame that could be output as a CSV with all of those values, just to make that a simpler process. So R is free, it's open source, which facilitates increased transparency, accessibility, and reproducibility of the science that you do. And that's a good thing no matter how you cut it. So the advantages to R is that analyses are actually pretty simple and straightforward. It can help you with designing your studies. It can help you, you can do power analyses or simulations if you have complex designs, something that GPower or whatever power software you use can't quite handle. There's extensive documentation for R usually, and even where there's not, there is an extensive online community where you can always get help. It's easy to connect direct to data sources, whether that's using SQL to pull directly from databases if the data that you're working with is too big to be all in one Excel file, or web scraping, just downloading data direct from an HTML link. And also the data wrangling, the data prep and cleanup part, which is 80% of data analysis, is 10 million times easier in R. Because of that, I argue that R can do things that SPSS can't do, but the opposite isn't true. And yes, R has a learning curve, but it's no harder of a learning curve than SPSS, especially since the learning curve of SPSS also includes default behaviors that are sometimes nonsensical and incredibly inconvenient, that even if you are aware of those under-the-hood default behaviors, you may have to use some asinine roundabout way to go around that. And because of all of that, I argue that R is a better, more useful tool for data science research and analysis. So what I would propose is a 3-hour course, R programming for psychological science, that's similar to the Ag Department has SAS for agricultural sciences as one of their graduate courses that they take the first semester. This would subsume drill, and instead of having just a 50-minute drill, it would be a 3-credit-hour course, so meeting for the same amount as a full course would. But it also includes everything that you would do in drill that first semester, but it has time to expand beyond just here's how to do this statistical test, and rather here's how we can learn to use R and have this as a tool in our tool belt that we can use on a number of things moving forward. Beyond that, I would argue that the simplicity of this general linear model, where it is just adding one thing at a time and continuously building on what starts with, okay, what happens if we predict just the mean for everything? I think that if there was a course that was designed around teaching R over the course of the semester, it'd be easy to be able to incorporate that into there. And so instead of just having a column of numbers and saying like, all right, get your calculator and sum up all those numbers and find your mean. Now create a second column where you subtract your mean from each of those variables. If it was just instead like, hey, here, create this vector of numbers. Now find the mean. Now create a new vector of numbers that's each one of those numbers minus its mean. So still doing the by hand method, only doing it on a computer via script rather than writing it out with pencil and paper. And then also, as always, I've mentioned before a couple times over the last few years the idea of putting together some sort of stats or methods group. And I'd still be interested in doing that if there was interest amongst other people, or having some sort of stats or R workshops in the department, whatever works for all of you. So that said, that concludes my presentation, and I thank you for your time and attention. My slides are available at my OSF page. You can either link it here at osf.io/5x9u4 or just snap a shot of this QR code with your phone. And that concludes my presentation.